So first one is
okay.
Yes.
So that was the last one.
Yes. It was to change the. Do you plan to take the full hour?
No, I only plan to take 15 minutes.
Okay, anyway, Min-Hsiu.
Okay. Okay. First of all, I'd like to thank the organizer for having me here. Today I'm going to talk about this new results that strengthen the strong subjectivity inequality, so improve operator inequality, and that will lead to another proof strong subjectivity. And I would like to thank my organizers. Jim David was my intern. He's a PhD student from UCSD, and I said from Davis. And I also would like to emphasize that the key insight of this very nice operator inequality was actually made by Jim David. You will see what it is. And I would also like to argue that this probably is the easiest talk of the whole week, because the things that has been used behind the proof is so basic. I assure you, you will be able to understand every line of this talk. And I'm quite confident of that. So contrary to like Marius, who give you a tough time yesterday before lunch, this is a very easy talk that would allow you to enjoy your benefit. Okay, so we all know that we have this symbol, this quantity that we call the entropy. Like in the classical regime is just given a probability vector, then you can compute this minus I sum over I, and then this corresponds with so-called content motion. The von Neumann entropy is that given the density operators, then you can compute the so-called content entropies, just minus trace rho log rho, and you could already see that by special decomposition, this content entropy is more general than the classical entropies. And I also didn't need to emphasize that this entropy plays significant roles in many areas, like from fundamental physics to coding theory, information theory, the cryptography, etc. I think this is like information, classical information theory 101. This Shannon entropy has very nice properties. So there are four of them. So this entropy is quantity is not negative, and it has this monotonicity properties. And the third and the fourth properties, subjectivity and strong subjectivity. So these are, like I said, this is very basic properties of Shannon entropy. The next question, like in our community, or the first few questions is that does this inequality hold for content entropy? And I'm sure that everyone here understands almost all of them. So the content entropy, the von Neumann entropy is still not negative, but in the content regime we don't have this monotonicity because of this entanglement. Like it's easy to construct a counterexample. If you think of rho AB is a pure state, the von Neumann entropy is 0, but if you look at the reduced density on either system A or system B, it's larger than 0. So in the quantum regime, monotonicity did not hold. Quite surprisingly, this seemingly very complicated in the sense that this strong subjectivity holds in the quantum regime. And of course, this is I would like to the main goal of this talk is of course that to give you arguably the easiest proof up to now. Okay, so this is a very simple. This is like the literature on strong subadditivity. And we all know that this result was first proved in 1973 by Leibs and Min-Hsiu Hsieh, that relies on a beautiful functional analysis result. So like Leibs proved that this matrix function has concavity properties, and then you can use that later on to prove the strong subadditivity. And of course, that after that, there are a few alternative proofs. I only list two of them, but if you look deeper, then there are 4 or 5 more, maybe. Secondly, kind of like a variant of this strong subadditivity is related, relates to this page recovery map. Like people started to look at states that could satisfy this strong subadditivity. So, and again, this many of the nice results in this region, and you can see that a few of the authors from those results was already in this conference in the authors. And then in 2012, Kim he in this not a very long paper, he proved another operator extension of strong subadditivity, which is given right here. The reason it's an operator inequality is that you notice that the trace is only subsystem B and C, so there's still this matrix part on subsystem A. And just kind of a side note that our operator extension actually recover Kim Isaac's this Isaac's operator inequality. I will show you how to do that after I give you the proof of our result. Okay. So even though this monotonicity does not hold for the content entropy, but this is a weak version of monotonicity, and people give it the name weak monotonicity. So so this is one of the so S rho AB minus S rho A, and this is the second part. This is still true. Okay. And the reason this is true is that this earlier counter example, like pure state, would not give you counter example anymore, because we all know that it's kind of like a property, a very fundamental property of pure state, like monogamy of dependence. So as long as rho AB is a pure state, then you will be able to make it further pure. So so this weak monotonicity is true in the quantum regime. Okay, and in fact, this weak monotonicity and strong subadditivity are equivalent, and this also has been discussed in the original paper by Leibs and Min-Hsiu Hsieh. It's easy to prove the equivalence. The key observation is that given this 4-party pure state, because of the duality, the von Neumann entropy of AB, the subsystem AB, is equal to like the remaining two. So it's equal to the von Neumann entropy of CD. And if you break it between subsystem A, B, C, and D, you have another set of qualities. And then either you start from the weak monotonicity and you rewrite this rho, so this von Neumann entropy on subsystem CD by AB because of the equality, and this rewrite this one by von Neumann entropy on subsystem rho ABC, and then you can recover strong subadditivity, and vice versa. So if you start from that and you put in this, and then you would get this weak monotonicity. Okay. So far we only talk about this scalar or the trace version, trace inequality. Right? So this is strong. Let me recap that. This is strong subadditivity, and this is weak monotonicity, and they are equivalent because you can write this psi ABC as a pure state and you can use this relation. What we want to answer is that could we generalize this trace inequality to the operator version? And it turns out that these two notions becomes inequivalent. So for the operator version of these expressions, it's easy to see, like if you take trace of rho AB of these whole things, you will recover strong subactivity. This is again very trivial. But this operator version is not true. I suppose that you could construct an easy example by just making rho ABC to contain an eigenvalue that is close to 0, right? And then this is minus infinity. And then this remaining 1 would be bounded away from 0. Then you would have examples that shows that this operator version of strong subactivity is 4. Quite interestingly, this operator version is true. And this is what we are going to prove in this talk. Okay, so far so good. Did I still keep my promise? Like everything here is easier. Okay, and then to prove this, it's literally a 3-line proof. I'm not kidding. It's very easy. So this is a preparation steps. This is the operator inequality we want to prove, right? And we can actually make it a stronger version by replacing rho AB and rho A by another state or sigma, any state, sigma. We do it here. So it's sigma BC and sigma C. So this is just to make it stronger. So this is easy to understand. And then I claim that if you have this operator inequalities, this would give you this operator inequality because this metric function log is an operator monotone, right? So if you take log of these things and then you rearrange, then you would get this operator inequality. So far so good, right? So it's also easy to just take log, right? This metric function is easy to calculate. Okay, then you might wonder, I hide all the difficulties into proof this operator inequality, right? But no, this is 3 nice proof. Remember that we want to prove this, right? Let me use this circuit diagram to prove. So the left-hand side, so it's equivalent to this. So this is rho BC. So these two graph in the middle is exactly rho BC, right? And this is rho A minus 1. Okay, so I just separate it into 2 parts, right? And then you could again rewrite. You can move these terms and make it a sandwich on this part. Good. So then we could kind of like rewrite it into this matrix less than identity. Okay. And then to show that this matrix form is less than identity is equivalent to just showing that this largest eigenvalue of one of that is less than 1, because this is like A and this is A and A data, right? So, and this is positive. So it's equivalent to just show that one of this A is have matrix, the operator norm is less than 1. Good, right? So nothing too fancy. And then from this circuit, you could just rewrite it. So it also doesn't. So you just rewrite this short line here by making it a longer line. Okay, and then cut it in half. Okay, so you will have this thing which is given here, and this other half looks like the dagger of this isometry. So the reason is isometry, you have to read it from the right. So A to A, B, and B dagger. From input A to A, B, and B dagger. Right? So this button, this one, I would argue is isometry. So I will prove that in one sentence in the next slide. But we see that this object can be divided into an isometry times this isometry taking dagger form. And we know that operator of like this operator of isometry dagger times isometry is less than 1. So again, it's very basic linear algebra. Okay, so now the plan is to prove that this is an isometry. Again, so this is a one-line proof. So to show that it's isometry, you just show that this dagger times this, right? So you make it this one, and this is an identity. So this is isometry. Okay, and the proof is complete. So this is the summary of the proof. We started from here, and we claimed that this operator inequality is to this operator with monotonicity. And then to show this, it relies to show that the operator norm is less than 1, and this because this is a we got it. So I hopefully I know that many of you would have to have like a lecture on content information and computation. I remember that when I delivered that at UTS, I had been debating whether I should include like a proof of this subadditivity or strong subadditivity in the lecture. But eventually I gave up because it's difficult to go over that convertibility of the trace inequalities. But now I believe that you could all show that to your students with the very basic linear algebra. Okay, so so like I said, I have completed the proof. What I want to do next is I have 2 other discussions. So the first discussion is that I claim that we can recover Kim's this operator inequality, and this is also a few lines proof. So starting from the operator inequality that I proved in the previous few slides, and just because this is this whole thing is positive, then you can sandwich it by any operators, right? So here for any operators on A, and you sandwich that, this is also larger than 0, right? And remember that this rho CD is the reduced state of this pure state side ABCD. So rho CD is equivalent to rho AB. This is dualities, and then you just replace the corresponding CD with AB, and then you could recover this segment. Okay, so it's also easy to see. So nothing fancy. Okay, I have one last slide. So people has been asking me like this operator inequality seems very easy to understand, and it also very strong because it bypass all of this very complicated proof in the literature. Are they useful, or would there be any useful applications? Indeed, there is one. So this result actually spun out of a project that I've been doing with David. Is that we all know that in Mario's talk, he defined this Markov state. Right? Markov state is the state that gives you 0 conditional mutual information in the quantum region. And we all know that if you go to the approximate version, this is not true, and that's why we have these studies on page recovery map. So one of our conjecture is that what other conditions that you have to put in so that we all know that we can construct a state that is that is not a state on ABC, that is not necessarily a Markov state, but we could argue that we still have give you conditional mutual information close to 0. So so this is what we're trying to prove. So if you argue that the conditional mutual information of AC given B and BB given C, then we could argue this. We hope to argue that this is close to a Markov state. And our proof strategy somehow go back to relies on this operator inequality that they prove. But again, this is still conjecture. We haven't finished the proof. But so I welcome you if you are interested in work on this. Okay. Thank you very much. So that's all. Before you all ask questions, let me ask question first. That I keep my promise. It's okay. Thank you.
Yes, so when you write the close to Markov state, because now we have more systems, so like Markov in what decomposition?
Yes. So it would be Markov in, I think in C in this case, but C and sorry, B and C
In both.
Yes.
Thanks. Yeah, question. Yes.
Also, thanks for the nice talk and very intuitive and nice alternative proof. But if I remember from matrix analysis, to prove that the low logarithm is operator monotony, usually it's theorem. The number I use it in my class, and the students don't have that background in matrix analysis to know which functions are operator monotony or not.
So Marius, could I direct the question to you? How to answer this?
Sorry?
No, I have to.
Yeah,
it seems that the hard theorems operated from that logarithms, right? That's what we showed.
Sorry?
It's reduced to the inverse.
Yeah.
The fact that x inverse is monotone, that's ruling that the rest is mixed. Sorry.
Okay.
You want something to go on? No.
I mean, I will not deny that your theory looks too good to be true. The fact that you can just choose the wrong sequence independently. I mean, okay, then you convince us it is true. Luckily, it's so easy. But is there not any kind of benefit from that? I mean, in the end, you just say, oh, choose the right to sequence. But I mean, there has to be something better. Can you do something different?
No, I mean, I has been asked, I think, by Curly and also by Marco. I don't know. So I mean, this will be open to you guys to give it a shot and let me know if you've got anything.
But I think you can even add more isometries into it, make more complex combinations, and it's still not useful.
Or
Yes.
So when the conditional mutual information is 0, we know that the state must form a Markov chain, right? Is it easier to see with this operator inequality, or that is still hard?
No, I don't think that would relate to the structure of it at this moment. But this is more related to what we want to prove here. So given this second approximate condition, we guarantee that as long as both of this conditional mutual information is close, then we could have this state close to Markov state. We don't know, but yeah.
But I guess what I'm asking is the step before this, right? When the conditional mutual information is 0, I guess this translates to the operator inequality holding with equal, right? And then is this Markov structure easy to see or not?
I think you could, in one way, you can show that. I suppose you can do that. I haven't do that myself, but.
The time. No, well, good. Then let's thank Min-Hsiu again.